So the last talk of the session will be given by Xiaolin Lin. The title is Dynamic Stage-Aware User Interest Learning for Heterogeneous Sequential Recommendations.
Good morning, everyone. My name is Xiaolin. I'm going to present our work, Dynamic Stage-Aware User Interest Learning for Heterogeneous Sequential Recommendation. Let's begin with the problem we study. We aim to predict the next item that a user is likely to purchase based on the interaction histories, a heterogeneous sequence. And there are many types of behaviors in our setup, such as add to cart, purchase. Since we aim to predict the purchase item, we treat the purchase as a target behavior, and the others are auxiliary behaviors. There are two challenges making this problem non-trivial. First, user interest is dynamically changing across different stages and have stage characteristics. For example, users in these figures have three strings of interest corresponding to tablet computers, earphones, and the keyboard or mouse. The user interest is often influenced by the previous stage, such as these AirPods is influenced by the previous iPad. And the second challenge is the heterogeneity of user behaviors. Different user behaviors have distinct impact on purchase behaviors. And treating all the behavior equally will result in suboptimal predictions. To address these challenges, we propose our methods. We propose our method, Dynamic Stage-Aware User Interest Learning, in short, DSUIL. It consists of 4 modules. A dynamic graph construction module, a dynamic graph convolution module, a behavior-aware subgraph learning module, and an interest evolving pattern extractor. This is the overview of our framework. Now I will introduce one by one. The first module, dynamic graph construction. As we want to model user interest in a stage-wise manner, we hold a basic assumption that user interests are more directly reflected in the purchase behaviors, and they are relatively stable during the auxiliary behaviors. So, we use the purchase behavior to partition the sequence into several subsequences. Then, the last items in each subsequence is purchase items, and each subsequence is a snapshot of a stage of user interest in a window. And then, we transform each subsequence into a subgraph. So, a dynamic graph is a sequence of subgraphs. We consider 2 types of edge connection between items, item transition patterns and behavior transition patterns. The second module, dynamic graph convolution. This model is to run the item representation and the cross-stage interest dependencies. We calculate attention between the neighborhood item in a subgraph. We consider both item transition and the behavior transition patterns to calculate 2 types of attentions. For the central item I, its neighborhood item I, we take their element-wise product result and then use a learnable vector to calculate the inner product with it. After calculating with all the neighborhood items, we use a softmax to obtain the attention weight with about the item transition pattern. Similarly, For the HR problem, we also consider attention weight between the item I and item j about the behavior transition pattern. Then we take their mean pooling result as the final attention weights. Considering that a user's current purchase interest may be influenced by the previous stage, they are typically reflected through the purchase behaviors. We design different aggregation approach for non-purchase items and purchase items. For the non-purchase items, we directly aggregate its neighborhood item embedding in the current subgraph. We use attention-weighted summation. For the purchase item, we design a cross-window dynamic aggregation module. This module leverages the purchase item embedding of the current subgraph, the purchase item embedding of the last subgraph, the stage representation of the last subgraph to capture the feature from the last stage. We call this feature as dynamic propagation features. We symbol it as Z. Note that the state representation we will introduce later. Then we calculate the mean pooling result of Z and the weighted summation of the neighborhood item embeddings. We take this result as our expected purchase item representation. The third module, behavior-aware subgraph representation learning. After the dynamic convolution, we can obtain the item representation in each subgraph. Then we introduce a prediction and behavior embedding matrix to consider predictional relationship and behavior information to obtain the refined item representation. We take item T as an example. We take the summarization of prediction and behavior embedding to concatenate with the orange item representation. And the projection and the active function are conducted on these results. As we want to model the user's behavior heterogeneities, we propose a purchase-oriented attention mechanism. We take purchase item representation as query vector to calculate the attention weight with each item in the subgraph. Then we aggregate the item representation in the subgraph to represent the user's interest in the current stage. And this H is we just mentioned about, the state representation. Note that there may be no purchase item in the last subgraph. So we need to treat the last item as the purchase item so as to learn the last state representation. Finally, the last module, interest evolving pattern extractor. We use the comma self-attention module to extract a user's interest evolving pattern across different stages. This is a well-known structure from transformer. Then we obtain the output of the self-attention module. We follow subtract and take its last vector to conduct item prediction score calculation. And this is the loss function of our methods. It is a comma cross-entropy loss. Now I'm going to start to introduce some experiment results. For the details of experiment setup, please refer to our paper. We first introduce some baselines. We compare three groups of baseline. The first group of baseline includes some homogeneous sequential recommendation. These methods do not consider behavior information. And the second group is about heterogeneous non-sequential recommendation. We also call it the multi-behavior recommendation. They consider behavior information, but they do not consider sequential information in the sequence. The third group of baseline is about heterogeneous sequential recommendation. They focus on the same problem as we studied. This is the overall comparison. Note that we conduct our experiment on two public data sets. They are all the e-commerce data sets. The one is Tmall and the other one is UB. From this table, the performer of our method is outperform all the baseline. This shows the effectiveness of our methods. We also performed an ablation study to assess a contribution of three models: cross-window dynamic aggregation module, behavior-aware subgraph representation learning, and dynamic graph construction. We can see that the performance degrades when we remove each model. This confirms the importance of three models in our methods. We partition the user's sequence within multiple windows, and each subsequence represents a stage of user interest. This process helps improve the performance. So we are curious about the influence of window number on the performance at first. So we conduct these experiments. We divide the user set into several subsets according to the window number, and then evaluate the performance on each subset. We also choose a baseline next IP for comparison. Specifically, we obtain 5 groups for each data set. For example, smaller than 5 means that this group of user sequence contains less than 5 subsequences. From these two figures, we can see that the performance of our methods is generally better on the groups with a related smaller window number. This suggests that our method is better at capturing the preference of users with relatively stable interest. We recall that our methods had a self-attention module to learn the user's interest evolving pattern. So in this part, we replace the self-attention model with other sequential models to explore whether our framework is compatible with other base models. Specifically, we replace it with GRU for REC, CASA, and FMP REC. From these two figures, we can observe that our method can enhance each baseline model and improve the performance. This shows the stronger compatibility of our methods. We draw a conclusion. We propose our novel framework, DSUIL, for heterogeneous sequential recommendation. We propose to represent the user's heterogeneous sequence as a dynamic graph to model a stage-aware interest. We design a dynamic graph convolution model to learn item representation and stage-wise and stage-level interest dependencies. We design a behavior-aware subgraph representation learning module to model the heterogeneity of user behavior and represent the user's stage interest. We leverage interest evolving pattern extractor to learn the user's overall interest for item prediction. Extensive experiments showed the effectiveness of our methods. That's all. Thank you.
Thank you, the speaker, especially that you finished just at the very last second of the time. So we have 2 questions. The most popular one is from the well-known Anonymous. The proposed approach seems overly complex. How tractable is in terms of computational cost and efficiency?
I'm sorry, can you please?
Yeah, sure. It's about computational cost and efficiency.
And I'm agreed that this framework seems to be complex. But we studied the heterogeneous sequential recommendation, and we try to present a user's heterogeneous sequence to learn the stage-aware interests. Therefore, we have to divide the sequence into subset sequence and construct some methods, construct some models to model each stage of interest. Therefore, we need to construct the graph and then construct convolution. And then we learn the state representation and to learn the user's overall interest. Thank you.
Okay, thank you for your answer. So this concludes the session. Remember that we're going to have coffee break now, sponsored by Netflix and Amazon Science.